In the previous example, we used the time-varying emission file, emit times, within the dispersion calculation to create air concentration and deposition output. In some cases, the emissions may be unknown, and therefore it is necessary to run high-split in a way that the time-varying emissions can be applied as a post-processing step. In this way, multiple emission scenarios can be tested and compared to measurements to find the best fit to any measurement data that might be available, without rerunning the dispersion calculation. In this simulation, we will automatically divide the simulation into 3-hour emission periods. But the particles released during each emission period will be automatically tagged with a unique pollutant identification corresponding to the release time. Therefore, each release time becomes its own element in the output concentration array. The files required for the simulation are mostly the same as in the previous section, except you will need to run the tcm_auto script and another emissions file, cfactors.txt, which is used in the post-processing step. The post-processing program requirements are different than the internal high-split calculations, resulting in a different format for cfactors and emit times. Looking at the script in more detail, the initial sections are the same as before. The control file changes only needed to reflect the requirement of a unit source emission rate that applies for a duration of 3 hours, which is repeated every 3 hours according to the Q-cycle namelist variable, which effectively results in a continuous emission. The setup.config namelist file has 2 additional variables. As mentioned previously, the emissions are cycled by defining a variable Q-cycle such that the 3-hour emission period is repeated every 3 hours. Also, setting the variable ichem equals 10 forces high-split to restructure the internal concentration array and output file from the default XYZ P dimensions, where P is for the pollutant, into the transfer coefficient matrix form XYZT, where T is for the different release times. In the default structure, the time variable is not needed because the array is zeroed after each output. In the TCM structure, concentration and deposition contributions from each release time can be identified. Now go ahead and execute the tcm_auto script. After high-split completes, continue with the post-processing and graphics. Before discussing the results, let's take a closer look at the high-split output file, tcm.bin. From the command line, run the conread program to show the details of the high-split concentration file. It can be found in high-split exec directory. However, your directory structure may be different. Notice how the 24 pollutants are labeled according to the release start time in hours and tenths relative to the simulation start time. Now we need to use the program tcm_sum to convert the unit source concentrations in tcm.bin to actual concentrations and deposition written to the file fdnpp.bin by adding together the concentrations from all the release time periods at each output time, thereby resulting in one pollutant output at each release or at each output time. One pollutant in this case representing all the 3-hour release times. The program has many options, which can be displayed by executing the program with no command line arguments. Most of the options are obvious, such as the name of the input and output files, the half-life in days, the name of the emissions file. For the others, because decay was not included in the high-split calculation, it is part of the TCM processing defined by the H argument, or half-life. The age would be the variable t in the equation, being equal to the time difference between the end of each sampling period and the fission stop time. The T031106 argument defines the fission stop time, the time of the earthquake, and which we already know is the valid time of the emissions inventory prior to any decay. If not present, this field defaults to the model start time, which in our case would have been March 14th. The C1 option selects column number 1 from the cfactors.txt emission file, which happens to be cesium-137. There is no limit to the number of columns in this file, and any column can be selected. However, if a gaseous species is selected, then the pollutant characteristics in the control file need to be modified from particle to gas. The PC137 option forces the replacement of the 24 emission time variables, hours and tenths of hours, in the pollutant ID field with a single field labeled C137. Otherwise, the graphics post-processing is the same as in the previous section. The time series, total deposition, and dose are almost identical, although slightly lower in the tenths field, to the previous calculation, which was done with no decay. The largest difference seems to be a very low cesium-137 prediction at the 9 UTC hour on the 15th at Tokai, which can be attributed to unneeded variability introduced by a too low particle release rate. Rerunning the calculation, this time at 10,000 particles per hour, results in a more consistent time series, but naturally at the cost of a much longer computing time. This approach, using an internal TCM output file, is limited to one pollutant species. Multiple species require the multi-output file approach, which will be addressed in the next section.